Yeah, hi, my name is Tor Leif Aarland. I'm a team lead within Nokia for product sales of radio products in the Nordic, Baltic, Benelux, UK and Ireland. Let's start with to understand how does electromagnetic waves propagate. What we see here is a base station, and we have a mobile unit here and an IoT device here. We can have signal going directly to the receiver or mobile, or we have signals that go via another object and reflects. The signal here may arrive in phase, and then we will see double power of the signal. It may also be the opposite phase, and then it can even cancel out the whole signal, so we don't receive anything here. And we also have signal that needs to penetrate through windows or even metal slot in cars. When the signal propagates, it spread out like this, and it distributes over a larger surface, so we lose the power per square meter of signal. And this is the formula. We don't need to dive too deep into it, but we see it, the losses of signal is proportional with the distance to the base station and the frequency, which means the higher frequency, the more losses we have. If we plot this versus the frequency, we will see that the losses increases logarithmically with frequencies. And the lowermost curve here is the 450 MHz. At a distance of 20 kilometers, we have a loss of approximately a little bit more than 50 dB. If we go to the higher frequencies, which are quite common in mobile network, 1800 or 2100, we see a loss of 65 dB, which is around 15 dB more. And 800 is also a popular IoT frequency. We see that there's something in between, around 55 dB. If we try to calculate how much signal will be received at the receiver end and plot that, what we have done here is that we have assumed approximately 40 watt transmitter, and we connect an antenna, and typically antenna have higher gain the higher frequency we have. But still the 450 is superior versus other frequency. We see at a distance of 20 kilometers we have a signal level of 10 dB milliwatt, while the 2100 or 1800 is around 0 dB milliwatt, which is okay, but this is superior. But what does this mean in coverage? We see that we have about 5 times longer cell radius with 450 versus 2100, if we just look at the free airspace losses. Then we have another thing that makes it even more complex. That is, we have to go through walls, windows to enhance the coverage. And going into a concrete building means more losses. Sometimes we are happy and the signal travels through the windows, but very often it goes through the concrete. Going into a wooden house, which we have quite much of in Sweden and the other Nordic countries, is not so difficult. It penetrates pretty good through wood and windows. Though very often when we have a water meter or electricity meter, quite often it's placed in the basement or location inside the house with poor coverage. So typically a basement can have a concrete wall of up to 30 centimeters, or you have bricks, which is around 25-30 centimeters. And also a common use case for IoT is trucks, excavator, and forest machines. They also can have quite high losses. If you look at the real values here, if you look in dense urban like Stockholm, Gothenburg, 450 MHz will lose 16 dB signal when it goes through the walls and windows. If you go to the 800, 900, which is also popular for IoT, we lose 2 dB more, and For 1800, 2100, we lose 4 dB more. 3 dB corresponds to 50% of the signal level. So we lose 50% of the energy when we have 3 dB more. Urban, we see it's less losses, and suburban, we have 10 dB losses. Still, 450 is superior to the other frequencies. And basement, which is in many houses a very important thing, but we see that's really hard to cover through the concrete walls. Sometimes the signal goes through the floor, from the ground floor and then down to the cellar, but very often it goes even through the concrete walls. And there you see we have quite heavy losses. Around 30 dB means 1,000 times. Vehicle is not so bad, but still, again, if you want to send some data over there, the network needs to predict what is the signal level I need to send with. But if the truck is driving, the signal level is changing all the time. But what we also see with 450, it's more evenly distributed signal. So still there, 450 performs better than the other frequencies. Then let's have a look at another phenomena, or 3 other phenomena with wave propagation. One is reflection. If the electromagnetic fields hit a surface that is significantly larger than its wavelength, the signal is reflected. Here we have an excavator, and let's imagine that the signal hits the arm or a junction at the arm. And with a high frequency, the signal will be completely reflected because the size of this part of the arm is so much larger than the wavelength. What happens if you go with a 450, which is much lower frequency? Then this becomes smaller than the wavelength. Wavelength of 450 is 67 centimeter. Then we see that the signal is scattered around. So we got something we call scattering. So if it hit a traffic light here or a traffic sign, the signal will scatter around, and it can even help us to cover this narrow street. But we also get some help from top on 450, because we have, on top of reflection and scattering, we have something called refraction. That is that the signal hit an edge that is in the same order of magnitude of size as the wavelength. Then the signal will simply bend off as refraction. This is also something we know from lights. And signal may even come from the side and refract into the street, and then you cover the street. So for 450 MHz, it has excellent propagation for different uses. Let's say you would like to survey a windmill with IoT. You would like to verify that the generator is running, the power it generates is fine, frequency, phase. You may survey the bearings of the shaft and verify that it's not deteriorating. You can do preventive maintenance. You know in advance when something is starting to develop. You cover the trucks going down in a hill or down in a valley, because the signal goes deep into valleys. It doesn't just go over like higher frequencies. Homes, housing can be IoT, can be metering, can be smart house. Power line, very often the power grid also needs surveillance. You need to verify the power current running here. You can do leakage current detection. You can verify the voltage. You can verify whether it's arcing. And it even covers helicopters, because it propagates so well in all directions. So let's have a look at what's happening with the 450 MHz frequency, because that's where we started a modern mobile communication. It started back in 1981, I think, with NMT. And it has been used for that. It has been used for private mobile radio and Tetra systems. And it's very popular. Many airports use it, many private companies, you have also municipalities are using it. So this is a very important spectrum due to its excellent properties. Here in the Nordic countries, we have been very happy because we have kept it for mobile systems, most of it. So it has been made available for mobile broadband and IoT in the Nordic countries. Some countries will use it for public safety like Spain. And also within public safety, we have many IoT devices that needs to be served. There is strong focus on this from industry, both users, operators and vendors. And it is an alliance that further developed the 450 ecosystem. We have the 450 alliance and standardization within 3GPP. When we get it standardized, device vendors will make it, network vendors will make it, and operators will make the 450. For Nokia, we see the 450 MHz as a very important band. It serving several critical use cases. We develop products and features for the band and even frequency variants due to the fact that this has been used for some private mobile radio. The 450 in some countries it's moved a little bit upwards, what's available. In some others it's a little bit downwards, but it is in the same area. So therefore we can make some easily make some new variants of the equipment we have. Thank you.